In this chapter, we are going to learn chemical kinetics. Let's start with the rates of chemical reactions. The reaction rate is defined as the concentration change over time, or the concentration change per second. Suppose we have a chemical reaction, hydrogen iodide decomposes into hydrogen gas iodine. Initially, we only have reactants, 0.84 moles per liter, no product. After 100 seconds, only 0.34 moles per liter of reactant left. The product, hydrogen, has 0.25 moles per liter formed, same as iodine. So what is the reaction rate? To calculate the reaction rate, we need to calculate the concentration change. For reactant hydrogen iodide, we use the final minus initial, 0.34 minus 0.84, that give you negative 0.5. For the product, is final minus initial is 0.25 minus 0, give you positive 0.25 moles per liter. Negative sign indicates concentration decrease. Reactant is consumed. Positive means concentration increase. The product is formed. Concentration increase. So to calculate reaction rate, we use concentration change divided by time. Okay, so time is 100. So divide by time. Here, divide by time, divide by time. So the reaction rate for reactant is negative 5 times 10 to the minus 3. For product is 2.5 times 10 to the minus 3. Okay, so this example shows that for a same chemical reaction, reactants, product, these different substances give you different rate. Okay, some faster, some slow. In this case, the hydrogen iodide reaction rate is twice as hydrogen gas, iodine gas. And this follows the stoichiometry in the reaction equation. Whenever you consume 2 hydrogen iodide, you form 1 hydrogen gas and 1 iodine. So the hydrogen iodide rate is the fastest compared to hydrogen gas and iodine gas. Okay, for reactant, because concentration decrease, so the rate is negative, and the product increase concentration, reaction rate is positive. Let's define rates for an arbitrary reaction such as this one. 1A, 2B forms 3C and 1D. For the reactants, okay, we define as rate of consumption. It's the concentration change for the reactants divided by time. Now we know that concentration of reactants decrease, so the change will be negative, and we put a negative sign in front of it so that the rate of consumption is positive. For the product, we call the rate of formation. It's the concentration of product change over time. Now from last slide, okay, the example, we showed that for a same reaction, the reactants product have different rate, some faster, some slower, but they follow the stoichiometry. So in this case, whenever you consume 1A, you will consume 2B, form 3C and 1D. So in this case, B, the rate must be twice A. C will be 3 times A. Now suppose the rate for A is 0.1 moles per liter per second. Then B should be twice of it, 0.2, and C will be 0.3, and D will be 0.1. So again, you see the different substance give you different rate. However, if you divide by the coefficient, for example, the B rate is 0.2, but if you divide by 2, the coefficient is 2, then you get 0.1. And for C, you also divide by coefficient 3, again you get 0.1. They all becomes the same. So here is an important feature. For a different substance, for a same chemical reaction, they different rate, but if divided by the coefficient, then they get the same number, and this number is called rate of reaction. Okay, so we have rate of consumption for reactants, rate of formation for product, they all be different. But if you divide by coefficient, you get the same number. And so the rate of reaction is used for the whole reaction. So for the whole reaction, we can choose any substance. We can choose A or B or C or D. The rate will be different, but we divide by its coefficient, then you get the same number, which is called rate of reaction. With rate of reaction, okay, we multiply by the coefficient, then you get the individual rate. So we can calculate rate for A or B or C or D. All right, just by multiply the coefficient of the rate of reaction. Here shows the conversion between the different rates. The rate of consumption is defined as the concentration change of reactants over time, and the rate of formation is the concentration of product change over time. Okay, for the reactants, the rate of consumption divided by 2, coefficient is 2, and that gives you the rate of reaction. Similarly, the product rate of formation divided by coefficient 3, okay, that gives you also the rate of reaction. Conversely, from rate of reaction, we multiply by coefficient. So times 2 give you rate of consumption, times 3 give you rate of formation. Sample question. If the rate of formation of NO is given, so NO rate is 0.16, what is the rate of consumption of NOBr and the rate of reaction? So in this case, what is given is the rate of formation NO, and we want to calculate the rate of consumption here. Okay, now we know that the rate of individual rate, if you divide by coefficient, then you get reaction rate. From reaction rate, then you multiply by the coefficient, then you get individual rates. So first we calculate rate of reaction. Okay, so rate of reaction is the rate of formation, right, of NO divided by coefficient 2. Okay, this is the rate of reaction. Okay, and then from this we can calculate NOBr just by multiply by the coefficient, which is also 2. All right, and that give you 0.16, okay, millimoles per liter per second. We just defined the reaction rate, but what factors affect reaction rate? Increased concentration will increase reaction rate. Increased temperature increase reaction rate. Add the catalyst also increase reaction rate. The rate law is an experimentally determined equation showing how reaction rates depends on reactant concentration. So usually the rate law is written as this equation. So in this equation, A, B are the concentration of AB. Usually they are reactants. K is called rate constant. Now the rate constant actually depends on temperature and the catalyst. So this equation looks like only depends on concentration, but in fact it's also affected by temperature, catalyst that included in the K constant. Now alpha, beta are the power of the concentration. These alpha, beta are called reaction order. Okay, for example, if the rate law is V equals Ka to the first power and B to second power, then we can say this reaction is the first order with respect to A, second order with respect to B. Okay, what's the overall reaction order? Okay, the overall is when you add 1 and 2 together. Okay, so the alpha and B added together is called the overall reaction order. So in this case, the overall reaction order is 3. Here is an example of a chemical reaction and the corresponding rate law. Note that in the rate law, NO2 is a second order, which does not match the coefficient of the equation, reaction equation. Similarly, here's another reaction with the corresponding rate law. Note that the rate law is very complicated. It's not the first order with hydrogen gas, not the first order with bromine. Okay, now these are called overall reaction. Okay, overall reaction only tells you what's the reactants, what's the product. It does not tell you what happened at the molecular level. Okay, for example, for the second reaction, maybe first step is bromine molecules first split into 2 bromide radical, and then bromide radical attack hydrogen gas, forms a product with a hydrogen radical, and then hydrogen radical attack bromine, forms another product. So at the molecular level, they may undergo many elementary steps, all right, and much more complicated. These elementary steps combined together is called mechanism. It is this mechanism that determines the rate law. Okay, so in order to get the rate law, we need to know either by experiment or by mechanism. You cannot infer from the overall reaction. This table lists the rate law, reaction order, and the rate constant. So whenever we see a first order reaction, okay, we should immediately write rate law, which equals V equals K times A. Okay, that's the first order reaction. And the zero order should be V equals K times A to the 0 power. Now anything raised to 0 power is 1, and so this equals K. So the 0 order rate law, V equals K. First order, V equals Ka. Second order, there are 2 types. Type 1, okay, is Ka squared. So that's the second order with respect to A. Overall is also second order. You can also write as Kab. So first order with respect to A, first order with respect to B, but overall is still a second order. These are both second order. And third order is KABC. So first order with respect to A and B and C, the overall is third order. The unit of K depends on the rate law. Remember, no matter whether it's first order, second order, third order, the reaction rate has the same unit, because the reaction rate is defined as the concentration change over time. So it's molarity per seconds. Okay, now molarity is liter per mole. Okay, and then per seconds. So these are equivalent, or you write as liter per mole per seconds. So these are equivalent. So if it's a 0 order, okay, then because the reaction rate equals K, so they have the same unit, and therefore rate constant unit should be just molarity per seconds, or liter per mole per seconds. But if it's the first order reaction, then the reaction rate should equals to K times A. A, the unit for concentration, is molarity. So K times molarity equals the reaction rate, which is molarity per seconds. All right, so cancel molarity. So the unit of K should equals to per seconds. Okay. Similarly, you can find unit for second order reaction. So here are the units that depends on the rate law, okay, of the K. Sample question. Given the following data of the reaction, so we have concentration, and the measured reaction rate. Okay, we want to find the rate law for this chemical reaction. Now, in general, the reaction rate law can be written as Ka alpha power. All right, we have only one reactants, so just A to the alpha power. So let's look at the concentration. Initially is 0.1, reaction rate 0.085. When the concentration changes to 0.2, the reaction rate goes to 0.34. So the concentration increased twice. The reaction rate increased 4 times. Okay, so what does that tell us? Alpha cannot be 1, because if alpha is 1, then reaction rate is K times A. Is Ka. So that means if A increased twice, reaction rate also increased twice. It's linear. So that can't be true. So alpha, what if alpha is 2? Then reaction rate law should be Ka squared. So now if A increased twice, then square becomes 4 times, and that makes sense. So that is good. Now let's look at the next data. If concentration goes to 0.3 compared to the first one, that's 3 times. And the reaction rate goes from 0.085 to 0.76, and that's 9 times. So if alpha is 2, then when A becomes 3 times, 3 square becomes 9, and that also is consistent with the experimental data. And therefore the conclusion is reaction is the second order with respect to the reactants. Reaction rate is defined as the concentration change over time, or the derivative of concentration with respect to time. Derivative in calculus is used as a measure of how a function changes as input change. It tells us the rate of change of one quantity compared to another. Okay, so if notation is dy dx, that's the derivative of y over x, or y prime derivative. Okay, so these are all the notations. Whenever a quantity changes in value, we can use calculus to model its behavior. For example, derivative of a position or a distance, okay, over time with respect to time is the object's instantaneous velocity. The derivative can be calculated by using the common derivatives described in this table. For example, if you have an object falls from rest and at time t its displacement s equals 490 t squared. In other words, the distance or displacement is a function of time, 490 times t to the squared. The question is, what's the velocity when time is 10 seconds? So we already know the velocity is the derivative of the distance or displacement over time. In this case, the displacement is 490 times t squared derivative over time. Because 490 is a constant, it doesn't change, we can move out of the derivative. So it's 490 derivative t squared over dt. Okay, we need to calculate this function t squared derivative over t. Looking at the common derivatives, here it says x to the nth power equals n times x to the n minus 1. So here x is t, n is 2. So this should be, according to this equation, should be 2, n is 2, times t to the 2 minus 1. And that gives you 2t. All right, so the answer is 2 times 490 give you 980 times t. And when t is 10, so plug in time. So at 10 seconds, the velocity should be 9,800 centimeters per second. Integration is the antiderivative or opposite operation of the derivative. So if the speed is the derivative of distance over time, then distance is the integration of the velocity over time. Okay, so here is the notation of the integration, and the fundamental theorem, okay, allows us to calculate the integration. Integration is about the overall change. Example, integrate function 3x squared plus 4x plus 1 when x changes from 1 to 5. Okay, to integrate this one, we first separate the integration to 3 of them. So integrate 3x squared, 4x, and 1. So note that constant doesn't change. So when you integrate, you can move out of the integration. So here we have 3 times integration x squared. Now x squared, we look at the common integer, which is integral, which is 1 over n plus 1. N is 2. So this should equals to 1 over 2 plus 1, x2 plus 1. So that is 1 over 3 times x third power. So that gives you this one. Similarly, this power is 1, so 1 plus 1 is 2, okay, to the second power. And a constant, the first integer, constant integral of the k dx is kx. So here, just 1 times x. All right, so that's integration. Now from 1 to 5, the fundamental theorem says that it should be final minus initial. Okay, so you use final is when x is 5. So 5 minus initial when x is 1. Plug in, and the answer is 176. Here's another example. Find the displacement of an object when time equals 2, it goes to time equals 3, if the velocity of the object has a function as this one. So velocity is a function of time. We want to find the displacement. Okay, so distance is the derivative with respect to time. Displacement is the opposite. It's the integration of the speed over time. So 980t, the integration. 980 is a constant, so we move out of the integration. All right, only integration t. All right, so here again using this one, here x equals t time, replace to x, and n equals 1. So 1 plus 1 is 2. So 1 divided by 1 plus 1 is 2. T to the 1 plus 1 is 2. Okay, so that gives you 490 t squared, time change from 2 to 3. And so again, final minus initial. Final when t equals 3 minus when t equals 2. That gives you 2,490 centimeter. Now let's come back to the rate law. So here is a general equation for rate law. And remember, reaction rate is defined as the derivative of concentration over time. Now the opposite operation of derivative is integration. So if we integrate, what we get is the concentration as a function of time. And this is called the integral rate law. So the rate law tells you how reaction rate change when concentration change. The integral rate law tells you what is the concentration at a certain time. Okay, one tells you reaction rate, one tells you the concentration. Let's begin with the first order reaction. So suppose this reaction is a first order reaction. You should be able to immediately write the rate law. Okay, what is the rate law for the first order reaction? V equals Ka. Okay. Now, in order to integrate this equation, we need to change V to the derivative form, because V is the reaction rate. which is the derivative of concentration over time. Now A is the reactance, so it decreases with time. That's why you have a negative sign to make this positive. Okay. Notice that the left side has two variables. Concentration is a variable, time is also a variable. In order to integrate a differential equation, we must separate these two variables so that each side can only have one variable. To do that, we times dt on both sides, so that dt cancel each other on the left side. So the left side only have a, but the right side still have two variables, a and t. So in order to move a to the left side, we divide by a, concentration, on both sides. So this will cancel on the right side. Okay, so that gives you this equation. The left side now becomes dA over A. Okay, that's only one variable A. On the right side is negative k dt. So here only t, time, is the variable. So the left side, one variable A. On the right side, one variable t. Integration. Now we are ready to integrate. And the concentration change from initial A0 to the final A when time change from 0 to t. Okay, so what's the integration? Left side. Okay, left side, the common integral have 1 over x dx. Integration is ln x. And therefore, the left side should be x is replaced by a, so it's the ln a. All right, it changed from initial to final, so should use final minus initial, and that can be simplified as natural log a over a0. All right, so that's left side. The right side, negative k, are both constant. So a constant integration is just the constant times the variable. In this case, is t. So it's negative k times t on the right side. And therefore, we have this integral rate law. And for the first order reaction, the integral rate law is natural log a over a0 equals negative kt. All right, it's the natural log concentration as a function of time. It's negative kt. Okay, so if you have a natural log, let's say ln a equals b, then you can write a equals e to the b's power. So with this equation, we can write the ratio of a over a0, initial concentration, should equals to the e to the negative kt. So then we multiply by a0 on both sides. You have this equation. The concentration of a at any time equals initial concentration times e to the negative kt. So concentration as a function of time. So both of this are considered integral rate law for the first order reaction. We just derived this integral rate law for the first order reaction, and that is the natural log a over a0 equals negative kt. Okay, this can be rewritten as natural log a equals natural log a0 minus kt. This equation resembles a linear equation y equals kx plus b. So in this equation, y is the function, so this is y, and this is x, and you have a slope k. All right, that's the slope, and this interception is b. So this is a linear equation. So compared to the first order reaction, then we can use ln a as y and t as x, okay, as the variable, but the slope is negative k. A negative k means it decreases with time. So we have this kind of equations, and these are the linear equation for integral rate law when the k changes. Okay, so when you increase k, all right, the slope becomes steeper. So this is the first characteristic of the first order reaction, and that is the natural log of concentration as a function of time is linear. and the slope is negative k. Sample question. At 600 Kelvin, the partial pressure of azomethane of the following reaction was given in the table. So initially, this is time, the initial pressure is 10 to the negative 2 torr. After 1000 seconds, the pressure reduced to 5.72. Okay, increase time, decrease the partial pressure. The question is it first order reaction or not? So from the last few slides, we derived the first order integral rate law, and that is the concentration natural log of concentration over time is linear, not the concentration itself. So here, for gas phase reactions, the pressure is proportional to the concentration. So we can think about this pressure as a concentration. Okay, instead of plotting concentration as a function of time, we need to plot the natural log of concentration. So we modify this table, all right, to natural log the concentration over initial concentration. So this is the initial, all right, you calculate the ratio, natural log, all right, calculate them, and then you plot the natural log of concentration over time. All right, indeed, we get a straight line, and this indicates that the reaction is a first order reaction. Okay, and the slope is negative 3.6 times 10 to the minus 4, which indicates the rate constant is 3.6 times 10 to the minus 4 per second. Okay, remember, the natural log concentration over time is linear, only valid for the first order reaction. If it's a second order reaction, then this is not linear. All right, you will see that not the natural log, but the inverse concentration as a function of time is linear for second order reaction. In kinetics, half-life is defined as the time it takes for the reactant concentration to decrease to half of its initial value. So let's calculate the half-life for the first order reaction. We start with the integral rate law. All right, that's the natural log A over A naught equals negative KT. Modify this equation so that we can calculate the time if we know the concentration. So here, when this concentration becomes half of the initial concentration, then we have, all right, negative 1 over K ln half of initial concentration divided by initial concentration. Note that now the initial concentration canceled each other. So we have negative 1 over K ln 1 over 2. So natural log 1 over 2 equals negative ln 2. And therefore this becomes ln 2 divided by K. So the final conclusion is the half-life for the first order reaction is ln 2 divided by K. Alright, so that's a very important characteristic for the first order equation reaction. That is, the half-life in this equation does not have the initial concentration. Initial concentration cancel each other. So half-life is independent of initial concentration. Okay, we'll see that other reaction order, the half-life changes if initial concentration changes, and therefore this distinguishes the first order reaction from other reaction order. Example, for a first order reaction, A goes to P, it takes 10 hours for A change from initial A naught to half of it. How much time it takes to go from A naught to 1/4 of the initial concentration? So to solve this question, we show two methods. Method 1, what is given is 10 hours to go from initial to half of it. And that's exactly the definition of half-life. So this is the half-life. Okay, it changes from initial to half of it. And from half concentration to 1/4, that's another half-life. And note that this is half-life because the final is half of the initial concentration. And we learned in the last slide that if it's a first-order reaction, then half-life is independent of initial concentration. So initial concentration A0, half-life is 10. When initial concentration is half A0, the half-life is still 10 hours. Okay, and therefore the total time to go from A0 to 1/4 A0 is 20 hours. Now in method 2, we use integral rate law. Okay, we can always use integral rate law to calculate the time if we know the concentration. But first we need to know the K constant. So whenever we have half-life, okay, we can calculate the K constant because in first order reaction, half-life equals ln 2 divided by K. So if half-life is 10 hours, then K can be calculated. All right, in the future, whenever you know the half-life for a first order reaction, you can calculate the K constant for the first order reaction. So plug into this equation, and also A becomes 1/4 A0, cancel A0. You can calculate time to be 20 hours, give you the same answer. Example, radioactive decay is an important example of a first-order process. Carbon-14 is a radioactive nucleus with a half-life 5,760 years. A live tree contains a constant amount of C14, which decay at a rate of 15.3 per minute. If a falsified wood is demonstrated to decay at a rate of 2.4 per minute, how old is the wood? Okay, first, using half-life, we calculate the rate K constant. Rate constant is ln 2 divided by half-life, and that gives you 3.81 times 10 to the minus 12 per second. Okay, so that's the half-life, the rate constant for this radio decay of carbon-14. The question is, how old is the wood? How old means the time. So to calculate the time, we use the integral rate law. The integral rate law modified, you can calculate the time if you know the concentration ratio. That's the final concentration, that's the initial concentration. Okay, now this question doesn't tell you what is the concentration of carbon-14 before the live tree died and after the live tree died at the present time. So it doesn't tell you, but it does tell you the decay rate. That's the reaction rate. Decay rate is 2.4 at the time that we want to investigate. So that's the time. And this live tree contains decay rate. This is the initial rate, because whenever the tree dies, that's the reaction rate, decay rate is still 15.3. And then after the tree died, then the tree cannot absorb carbon-14. So the concentration will decrease and will become smaller. So 15.3 is the initial reaction rate. So we can write two reaction rate. Okay, one is initial, which is rate constant times initial concentration of carbon-14, which is 15.3 per minute. And at the present time, the K times concentration equals 2.4. So if this is 1, this is 2, and we use 2 divided by 1, and you will see the rate constant cancel each other. So we get the ratio of the concentration over initial concentration, give you 0.157. This plug into the integral rate law, and we can calculate the time. So the time is calculated to be 15400 years. Summary of a first order reaction. So suppose A goes to P is a first order reaction. The rate law equals Ka, and the reaction rate can be written as negative derivative of a over t, you get a differential equation. Integrate this equation, we get integral rate law. For the first order reaction is natural log a over a naught equals negative kt, or concentration A equals initial concentration times e to the negative kt. Okay, now if we plot natural log a over a naught versus time, you should get a straight line. The slope is negative k. And the half-life for the first order reaction is ln2 divided by k, which is independent of the initial concentration. Here shows some examples of first order reactions. So these are all gas phase reactions, and the measured rate constant are given. The half-life can be calculated. All right, so use ln2 divided by k. You should be able to get this half-life. So when you calculate, the unit is seconds. I need to change to minute or hour. We just discussed the first order reaction. What about a second order reaction? Suppose A goes to B is a second order reaction. Then the rate law becomes Ka squared. And again, to integrate this one, we need to change V to derivative of A over T at the negative sign. So this becomes a differential equation. And then we separate the variables. So we times dt to remove time in the left side, and we divide by A squared, so that the right side can only have T, but the left side only have A. So you have this equation, and integrate from A naught to A. So the right side is a constant, so it's just kt. The left side is have a standard integral. It's 1 over x squared dx integration. That should be negative 1 over x. And therefore, we have the integral rate law is 1 over a minus 1 over a naught equals kt. Okay, or you can write 1 over a naught equals 1 over a equals 1 over a naught plus kt. Okay, so compared to the first order reaction, first order is ln a over a naught equals negative kt. So here is the inverse a minus inverse a naught equals kt. We just derived the integral rate law for the second order reaction. That is, the inverse concentration minus inverse initial concentration equals kt, or inverse A equals inverse A naught plus kt. Compare with the linear equation. If we replace y by 1 over A and x by t, then we also get a straight line. So we need to plot inverse A versus time. Okay, so you get a straight line, and the slope is the rate constant k. So these are the k constant. Okay, now compare with the first order reaction. In first order reaction, it's the natural log A versus time is a straight line. For the second order reaction, then it's the inverse concentration versus time is a straight line. What is the half-life for a second order reaction? To calculate half-life, we start with integral rate law, and then we modify it so that we can calculate the time if we know the concentration. So when the concentration becomes half of the initial concentration, so this equals 1 over k, 1 over this A becomes half A naught minus A naught. All right, then 1 divided by half A naught equals 2 divided by A naught. Okay, and therefore we have this equation. So 1 over k, 2 divided by A naught minus 1 divided by A naught. So 2 minus 1 is 1. So we have this conclusion. The half-life for a second order reaction is 1 divided by K divided by A naught. Note that in this equation you have initial concentration. When you change initial concentration, half-life changes. And that's for second order reaction. For the first order reaction, remember, half-life for the first order reaction is ln 2 divided by K constant, only depends on K. There's no initial concentration. For the second order reaction, it also depends on K constant, but also has an initial concentration. So first order reaction is independent of initial concentration. Second order half-life inversely proportional to the initial concentration. So if you start with a concentrate solution, this is large number, then it takes a shorter time to go half of it. And later, when the concentration becomes dilute, becomes smaller, then it takes longer time to consume half of initial concentration. This is an example we already talked about for a first order reaction, but now let's look at the second order reaction. So if we know the reaction takes 10 hours to consume half of initial concentration, does it take 20 hours, okay, to go from initial to 1/4? Now, for the first order reaction, this is 20 hours. But what about the second order reaction? So here, from A naught to half of it is 10 hours. That's a half-life. But here, from half A naught to 1/4, that's another half-life. All right. So if it's a first order reaction, then half-life is independent of initial concentration, so it should be 10 hours. But if it's a second order reaction, we just learned that half-life is inversely proportional to the initial concentration. So this is initial concentration, half-life is 10 hours. When initial concentration becomes half of it, then this equation tells you the half-life should be longer, should be twice, okay? It's inversely proportional. So if initial concentration becomes smaller, then it becomes longer half-life. It's twice, so that should be 20 hours here. And so the total should be 30 hours. Here's another example. A reaction believed to be either first order or second order has half-life 20 seconds at the beginning of the reaction. So that's a half-life at the first, but a half-life of 40 seconds sometime later. So during the reaction, the half-life changed because the concentration changed. So what's the order of the reaction? Well, apparently it cannot be first order, because if it's first order, then it doesn't change when you change concentration. So if you measure 20 seconds half-life at the first beginning, then later it should still be 20 seconds. Now the fact that it changes, all right, says that it cannot be first order. So it has to be second order, okay? Yes. When deriving the integral rate law for the first order and the second order reaction, we assume the coefficient in front of reactants is 1. What if there's a coefficient in front of A is not 1, for example 2? Okay, so what is the rate law? What is the integral rate law? So first we write the rate law, which is, if it's a second order reaction, it's Ka squared. That's the second order reaction. But this rate is the whole reaction rate. For A, it should be twice of this one, okay, because you have 2 in front of it. So the differential equation is the derivative of A over T. A over T should be 2 times K times A squared. Okay. Now if we combine 2 times K, all right, together and give a constant called K effective, all right, then we have a differential equation. The negative dA over dt equals K effective A squared. Now this is the same as this one. So if it's 1, then if you go back, you will see the integral rate, the differential equation is negative dA dt equals Ka squared. So they have the same format, all right, except this is a rate constant, this is effective rate constant. So all the results we obtained from this equation here will apply here. The only thing you need to do is replace K by K effective. For example, the half-life here we derived is 1 over K A naught. This is half-life, all right, but here it should be 1 over K effective times A naught. That's the half-life for this reaction. What is K effective? Is 2 times K. 2 times K. All right. Similarly, the integral rate law should be 1 over A minus 1 over A naught equals K effective times T. Example. If we have a chemical reaction, we want to find out if this is a first order or second order reaction. What do? You do experiment, measure the concentration change over time. So this is the concentration of reactants, and this is the time. Now, we learned that whether it's first order or second order reaction, the characteristics is not concentration with time. It's the natural log for the first order reaction. It's the natural log A concentration over time is a linear equation. But if it's a second order reaction, then it's the inverse concentration over time. It's a linear equation, okay? And therefore, in order to find its first order or second order reaction, we want to plot both of these plots, okay? Natural log and the inverse. So in this table, we add 2 columns. One is to calculate the natural log of this concentration. And the last one is inverse of this one. And then we plot both of this over time. Okay, so here are the 2 plots. And you can see the inverse is a straight line, but the natural log, the blue one, is the natural log, which is not a straight line. That means it's not a first order reaction, but it's a second order reaction. And the slope is calculated to be 0.775. That's the rate constant for this second order reaction. Suppose a second order reaction involves 2 different substances. Okay, this is called type 2 second order reaction. The rate law is K times A times B, and the differential equation is negative dA over dt equals K times A times B. So here we have 3 variables. We have time, we have A, we have B. So 3 variables. But A and B are related by stoichiometry. So if we assume the reacted A or B is X, because A, B, the reacted A or B are the same. So if X is the reacted A or B, then at any time the concentration of A equals initial concentration minus X. For B is initial concentration B minus X. So plug in this equation. Now we only have 2 variables. Okay, X is a variable that reacted, okay, A or B, and time is another variable. Okay, and separate variables, and we can integrate, and the final solution is this one. So this is the integral rate law for the type 2. So 1 divided by initial concentration B minus initial concentration A, natural log the concentration of B divided by initial concentration B divided by initial concentration A divided by initial concentration A naught equals KT. Okay, so this equation is valid when initial concentration A and B are different, because if they are the same, then this becomes 0. So 1 divided by 0 is infinity. Okay, so what if initially you add same amount of A or B? Okay, what happens? All right, you cannot use this equation. But if you look at this equation, all right, if initial concentration of AB the same, then at any time they're always the same. So A equals B, and therefore this equation you can write as Ka squared. And that go back to the type 1 second order reaction. Just A, you don't need B because they are always the same, just Ka squared. And therefore you go back to the type 1 second order reaction. Here's a summary of second order reaction. So for type 1, the rate law is just Ka squared. And this is the differential equation. Separate variables, integrate. This gives you the integral rate law, which says the inverse concentration of concentration minus initial inverse concentration equals Kt. If you plot the inverse concentration over time, you get a straight line. The half-life is 1 over Ka naught. So half-life is inversely proportional to the initial concentration. For type 2, involves two different substances. The differential equation is Ka times B. The integral rate law, here is the integral rate law, which applies when initial concentration AB are different. If they are the same, then you go back to the type 1 second order reaction. Here is a summary of integral rate law. For the first order reaction, the rate law is Ka. The integral rate law is this one. Now in class, we derived integral rate law is ln A over A naught equals negative Kt, or ln A naught divided by A equals positive Kt. So the concentration of A can also be written as initial concentration minus the reacted concentration. And so you will see this is equivalent to the one we derived in class. All right. The half-life of the first order reaction is ln 2 divided by K, which is independent of initial concentration. Now for zero order reaction, the rate law is just K. And in a homework, you're going to derive the rate law and the half-life. For a second order reaction, type 1, the rate law is Ka squared, and this is the integral rate law. And you will find this is equivalent to the one we derive is inverse concentration minus initial inverse concentration equals Kt. Okay, these two are equivalent. And the half-life for the second order reaction is 1 over Ka naught, inversely proportional to the initial concentration. This is the rate law for type 2 second order reaction, which is Ka times B, and here is the integral rate law. So when initial concentration A, B are the same, then you go back to the type 1 second order reaction. The reaction rate law tells us how reaction rate changes when concentration changes. But what is the temperature dependence of reaction rate? It turns out that temperature affects the rate constant, and the equation to relate rate constant to temperature is called Arrhenius equation. So here is the rate constant, here is temperature. All right, so rate constant K equals A, which is a constant, times e to the negative Ea over RT power. Okay, so that's called Arrhenius equation. Now we can modify this equation by taking natural log on both sides. Natural log K equals natural log A times e to the negative Ea over RT. And this equals ln A plus ln e to the negative Ea over RT. And ln e to the negative Ea over RT is just the negative Ea over RT. So we have another way to write Arrhenius equation, and that is ln K equals ln A minus Ea over RT. Okay, again, Ea is the activation energy, and A is called a pre-exponential factor or frequency factor. Okay, now this equation resembles a linear equation y equals kx plus b. So here y is ln k, okay, is y, and t here is the variable, so 1 over t. So x here is 1 over t. And then EA over R is k. So negative EA over R is the slope. Okay, that's the slope. And ln A is the B. So if we plot natural log k over 1 over t, and then we get the slope is the negative EA over R. The interception is ln A. So this is a one way experimentally determine the activation energy and the A constant. So if we measure at a different temperature, the K constant, so T1, K1, and T2, K2. So you have ln K2. You plot ln K over 1 over T, you get a straight line, and that's how we can find the activation energy and the A constant. The transition state theory tells us that before reactants forms product, it has to go through a high energy transition state and then becomes product. A transition state is an activated complex that can break up to form product. And here is a plot. This is the reactant and this is the product. Before it forms product, it must go through a high energy. That's the transition state. Okay, the energy between reactants and the product, and this energy is called activation energy. This is the minimum kinetic energy the reactants must have in order to form product. In other words, reactants must overcome this energy barrier to become product. Okay, so not all molecules has enough energy to overcome this energy barrier. Suppose you can reduce the energy barrier. In other words, you have a smaller activation energy. Then more molecules will have enough energy to overcome this energy barrier, and the reaction goes faster. So the smaller the activation energy, the faster the reaction it goes. Collision theory tells us that there are several requirements for the reaction to take place. One is collision requirements. That is, the reactants must meet, they must collide to form the product. So we can expect the reaction rate to be proportional to the collision frequency. And the collision frequency is proportional to the concentration. And therefore, the higher the concentration, the larger the frequency, collision frequency, the faster the reaction goes. And the second requirement is that molecules must have a certain minimum energy. That's the energy requirements. Okay. Now, collision may not lead to reaction unless kinetic energy exceeds a minimum energy. In statistics, we show that if we have a collection of molecules, large number of molecules, these molecules will not have the same energy. Some has high energy, some has low energy. The percentage of the molecules that has a certain energy E will be described by this equation, E to the negative EA over RT. And therefore, in other words, in the Arrhenius equation, the E to the negative EA over RT represents the percentage of molecules that has energy overcome energy barrier, EA. All right. The third requirement is the collision must be along a favorable orientation. That's a steric requirement. Not all directions can lead to the product. Only a certain angles that can lead to the product. Example: the temperature dependence of rate constant for a specific reaction is listed below. Okay, what is the activation energy and Arrhenius pre-exponential factor A. So we want to find the EA and A for the reaction. This is the experimental data. The rate constant measured at a different temperature. Okay, so Arrhenius equation tells us that the rate constant equals A times e to the negative EA over RT, or if we take natural log, we have ln K equals ln A minus EA over RT. If we plot ln K versus 1 over T, then we should get a straight line. The slope, from the slope, we can calculate negative EA over R, and the interception is ln A. So in order to plot ln K over 1 over T, we add two columns, all right, in the table. So one is 1 over T. So this is 1 over T. Okay, you inverse this temperature, but you should use absolute value, temperature. Okay, and the other is ln K. So ln of this column, you get this one, and then plot ln K over 1 over T, and that's the plot. All right, so you can see it's a straight line, and the slope, okay, the equation, all right, is this one. So that's the equation from this plot, and we find the slope, which give you slope give you activation energy 52.4, and the interception 14.1 give you natural log A, and so A constant can be found. Arrhenius equation tells us how the reaction rate constant change when temperature change. Suppose we have at T1 we measure the rate constant is K1, and we can write Arrhenius equation ln K1 equals ln A minus EA over RT1. But at T2 the rate constant becomes K2, so we write another Arrhenius equation. Note that A doesn't change, activation energy doesn't change. The change is temperature and K2. Suppose this is equation 1, equation 2. If we use 2 minus 1, then ln A cancel each other, and we have ln K2 minus ln K1, and negative EA over RT2 minus negative becomes positive EA over RT1. And we can factor out negative EA over R, and we have this equation. So natural log K2 divided by K1 equals negative EA over R 1 over T2 minus 1 over T1. So this is another version of Arrhenius equation. The advantage of this equation is that we don't have A. You don't need A constant. So all you need is activation energy. So if you know activation energy, and if you also know 1K constant at T1, then you can calculate K2 at a different temperature. Now this equation reminds you some equations we learned in Pchem 1. For example, the Clapeyron equation says ln P2 over P1 equals negative delta H vaporization enthalpy 1 over T2 minus 1 over T1, right? So this tells you at a different temperature the vapor pressure of the liquid at a different temperature. Another equation is a Van Hoff equation, ln K to K1 equals negative R delta H reaction 1 over T2 minus 1 over T1. So this equation allow you to calculate equilibrium constant. Note that this is capital K. It's the equilibrium constant at a different temperature. This is reaction enthalpy. But this equation is Arrhenius equation, so this K is rate constant. So rate constant instead of equilibrium constant at a different temperature.